Hello. Welcome once again. In this video series, you learn how to develop wonderful games using Unreal Engine 5 and its blueprint visual scripting, from the single node to the most complex function. In the previous video, we discussed creating a project and an initial level using a first-person shooter template. You then set up a target object that reacts to the player's gunfire by changing its appearance. We are going to look at how to add mobility to objects and their position to give a real effect. Please like this video if you find it helpful and informative, and subscribe to our channel for newer updates and game development tutorials. So let's start. Now that we have a target that responds to the player shooting, we can add some sort of challenge to start making our project feel like a game. A simple way to do this is to add some movement to our target. To accomplish this, we will first have to declare that our target actor is an object that is intended to move, and then we need to set up logic within the blueprint that will manage how it moves. Our goal will be to make the target box move back and forth across our level. Now we will work on changing actor mobility and collision. To allow our target to move, we first have to change the actor's mobility setting to movable. This allows an object to be manipulated while playing the game. From the main editor view, select box target_blueprint and look at the details panel. Underneath the transform values, you can see a toggle for mobility. Change this from static to movable. By default, basic actors that are placed in the world are set to static. Static means that the object cannot move or be manipulated during gameplay. Static objects are significantly less resource intensive to render, and this should be our default choice for non-interactive objects, so that we can maximize frame rates. It is important to note that the version of the target box that we changed in the level is just one instance of the blueprint template for the target boxes that we have created. An instance refers to an actual object that has been created, whereas our blueprints are descriptions of the kind of features that those instances will have once they are created. Any changes we make to a target box already inside the level will be made for that particular target box only. To make changes to all future targets, we need to modify the blueprint directly. To do so, open box target_blueprint again, either by navigating to the Open tab in the editor or by double-clicking on the box target_blueprint file in your content folder. With the blueprint open, we want to navigate to the Viewport tab located underneath the menu toolbar. Along the left side, you will see the Components panel, which lists all the components that make up this blueprint. Since we want to edit a property of the physical object, or mesh, we click on Component Static Mesh Component. You will see a familiar-looking details panel. It includes the same properties and categories that we saw when we edited the target box in the level editing interface. Here, we have to switch the same mobility toggle, located beneath the transform properties, from static to movable. This will ensure that all future targets created from this blueprint will already be set to be movable. Because we want to target this object with our gun, we also need to ensure that the target is capable of being collided with so that our bullets don't pass through it. Still, in the Details panel, find the category called Collision and look for collision presets in the drop-down menu. There are many other options in this drop-down, and by choosing the custom option, you can even set the object's collision interaction with different object types individually. For our purpose, we just need to ensure that this drop-down menu is set to block all dynamic, which ensures that the mesh will register collisions with any other object that also has a collider. Now that we have made our target movable, we are ready to set up blueprints that tell the box target how to move. In order to move an object, we will need 3 pieces of data. Where is the box target currently? Then what direction is it supposed to move in? And lastly, how fast is it supposed to move in that direction? To understand where the object currently is, we need to get some information about the world itself. Specifically, what are the coordinates of the box target in the world? The speed and direction are the values we are going to provide to the blueprint, though some calculations. And those will be necessary to turn those values into information that is useful for the blueprint to move the object. Now we will see the storing data with variables. The first step is to create the 2 variables we need, direction and speed. Go to the right-hand side panel labeled My Blueprint. You should see an empty category marker called Variables, with a plus sign to the right. Click on that plus sign to create your first variable. In the Details panel, you will see a series of fields for editing your new variable. The 4 fields that we have to edit are the variable name, variable type, editable, and default value. We want our first variable to contain information about the speed of movement, so name the variable speed. For variable type, we want a variable that can hold a number that will represent our desired speed, so select float from the drop-down menu. Check the box next to editable to enable the variable to be changed outside of this blueprint. This will be useful for quickly adjusting the value to our liking, once we start testing the moving target in the game. The default value category will likely not have a field, but will feature a message asking you to compile the blueprint first. Do that, and a field for entering an initial value will appear. Change the default value to 200.0. Using the same process, create a second variable called direction. Choose vector for variable type. A vector contains information about the x, y, and z coordinates, and in this case, we need to indicate the direction of change we want for the object movement. Make the direction variable editable and set default value to -10.0 for the y-axis. We will now explore the steps necessary to get the information we need to provide a movement instruction. It might look intimidating at first, but we will break down each section and see how each node fits into the larger goal. The first calculation we need to perform is to take our vector value for direction and normalize it. Normalizing is a common procedure in vector math that ensures that the vector is converted to a length of 1 unit, which will make it compatible with the rest of our calculations. Fortunately, there is a blueprint node that takes care of this for us. Click on the direction variable we created in the My Blueprint panel, and drag it into empty space in the event graph. A small pop-up will appear, prompting you to select Get or Set. We want to retrieve the value we set for the direction, so choose Get to create a node containing the direction variable's value. Click on the output pin of the direction node, and drop it into empty graph space. Type Normalize in the search field and select the Normalize node underneath the category labeled Vector. This will connect your direction variable to a node that will automatically do the normalizing calculation for us. To make our speed value relate to direction, we first need to multiply it by delta time. Delta time is based on the fact that the time taken between the frames of the gameplay can differ. By multiplying our speed value to delta seconds, we can ensure that the speed at which our object moves is the same, regardless of the game's frame rate. To do this, drag the speed variable onto the event graph and choose Get to create the speed node. Now, right-click on empty graph space and search for delta. Select the Get World Delta Seconds option to place the corresponding node. Finally, drag the output pin from either the delta seconds node or the speed node, and drop it into empty space. Type an asterisk in the search field, Shift+8 on most computers, and select the float node. Finally, drag the other output pin onto the remaining input pin of the new multiplication node to multiply these two values, like this. Now that we have a normalized vector direction and a speed value relative to time, we need to multiply these two values, and then add them to the current location. First, find the static mesh component from the Components panel, and drag it onto the event graph. This will create a node from which we can extract any data contained within the mesh component of the object. Next, we want to get the mesh's location. One of several ways to handle this is to look at the transform properties of an object and extract the location from there. Click and drag the blue output pin into empty space, and then type Get World. Select the Get World Transform option to create the node. A transform contains information about the rotation and scale of an object, in addition to its location. This will be useful because we want to ensure that we preserve the rotation and scale of our target even as it is moving, and we will need that data to create a transform value from our new movement information. Now we want to break down the transform into its component parts so that we can use just the location in our calculations, while preserving the rotation and scale. Drag the output pin from the World Transform node, and search for the Break Transform node to add to our graph. Now we need to add the necessary nodes to add speed and direction to the location information we just extracted. Right-click on empty grid space and search and select the Make Transform node. This will mark the end of your calculations, so make sure that it is positioned to the right of all of your other nodes. The Make Transform node has three inputs: location, rotation, and scale. The rotation and scale inputs should be connected to the rotation and scale output pins on the Break Transform node we created earlier. Next, we need to multiply the direction vector in the speed float we calculated. Our final calculation step is to add speed and direction to the current location we calculated. Click on the yellow vector output pin of the new multiplication node, and drag it onto empty space. Search using plus and select the vector plus vector node. Ensure that one input pin of this addition node is connected to the previously mentioned vector multiplication node, and then connect the other input pin to the location output pin of the break transform node. Finally, drag the output pin of our addition node onto the location input pin of the make transform node. When you are finished, the result should look like this. Now that we have the transform calculated, we can adjust the location of our target actor by this value. We used delta time to make our speed and direction changes consistent across frames, and as a consequence, we can simply use the event tick node to fire our move action every frame. Right-click on empty grid space, search for event tick, and place the node somewhere to the right of your make transform node. To move the actor, we will be using the set actor transform node. Drag a wire from the execution pin of event tick to empty grid space and search for set actor transform. Place the node and then connect the return value output pin on your make transform node to the new transform input pin on the set actor transform node, as shown here. Now compile the blueprint, save, and play the game. What would you expect to see? The box target would move according to our speed and direction as soon as the game began. However, since we don't have any instructions that cause the target to stop moving, it would proceed in the same direction for as long as the game runs, even moving through objects and out of the level we created. To address this, we need logic that will change the target's direction periodically. This will result in a target that moves back and forth between 2 points regularly, much like a shooting gallery target. Drag the direction variable into empty grid space and choose the set option. This will result in a node with X, Y, and Z axis fields. We can use them to change the value of the direction variable, which will be different from the initial default value. We want 2 of these nodes, so drag the direction variable again into empty space, and then change the y-axis values of the 2 nodes to 10.0 and -10.0 respectively. Now we need a way to switch between these 2 nodes, so that the direction repeatedly shifts. The flip-flop node was created for scenarios where we know we want to alternate between 2 sets of actions that execute exactly once before switching each time. This fits our use case here, so right-click on empty grid space and search for flip-flop. Select and place the node. Then connect the A execution pin to one of the direction set node input pins, and the B execution pin to the other. Finally, we need to ensure that there is some kind of delay between executing the direction shifts. Otherwise, the direction will change for every frame, and the object will go nowhere. To do so, drag the input execution pin of the flip-flop node into empty space, and search for the delay node. This node allows us to set a delay duration, in seconds, that will postpone the following execution commands, by that length of time. Place this node before the flip-flop node, and give it a duration of 6 seconds. Placing this delay node between our set actor transform node and our flip-flop node, will ensure that the direction switch enabled by flip-flop will occur only every 6 seconds. The final product should look like this. Once you are done, remember to compile and save the blueprint. Testing moving targets. Now that we have our blueprint updated, we can test to ensure that the box target object moves as expected. First, we will have to place the box target object in a position that will allow it to move along the y-axis without bumping into other objects. The coordinates used were 410 on the x-axis, 680 on the y-axis, and 180 on the z-axis. Note that these values will only work relative to the default layout of the first-person template map. If you have made adjustments to your own level, then you can adjust either the speed or the placement of the target in your level, and test until you find a good patrol spot. Click on play. If the blueprint is functioning correctly, you will see the box target move back and forth between 2 points at a steady rate. One of the advantages of using blueprints is that they create a template of functionality that can be used across multiple objects in a scene. Find boxtarget_blueprint in the blueprints folder and drag it directly onto 3D viewport. You will see another box target created, which inherits all of the functionality of our original box target. In this way, we can rapidly set up multiple moving targets using the single set of blueprint logic we created. So in this video, you set up a blueprint that will allow you to rapidly create moving targets. As we continue building our game experience, remember that you always have the opportunity to linger on a section and experiment with your own functionality or customizations. One of the greatest benefits of Blueprint's visual scripting is the speed at which you can test new ideas, and each additional skill that you learn will unlock exponentially more possibilities for game experiences that you can explore and prototype. Hope from this video you will start to move into building in more advanced mechanics in an easy to follow step-by-step approach which will allow you to play around and build your own content to eventually build your own game. Thanks a lot, see you in the next video.